In our last lesson, we introduced a variety of stereoisomers, that is, molecules that have different orientations in space. In this lesson, we're going to talk about ways that we can represent stereoisomers systematically, so they are easier to compare. The first that we'll talk about is the Fisher projection. These are really important for our understanding of carbohydrates in particular. In a Fisher projection, we follow a set of rules for orienting each chiral center so that every time we draw the molecule, it is in the same orientation. The first rule is that we are always going to have the main chain of carbons oriented vertically, with n numbered 1 on top. Every time the bonds come together in a cross, that represents a chiral center. The vertical lines at this center are interpreted as pointing away from the viewer. Look at the orange and red spheres in the model drawn to see what this looks like in a ball and stick model in 3 dimensions. Notice the Fisher projection itself has no formal indication of this. It is assumed of the structure. If there are two groups pointed back in a tetrahedral center, the other two, the horizontal lines, are interpreted as coming toward you. Your book says this looks like a bow tie. While I like this reference, I always like to think about the sidelines as opening their arms for a big hug. Whenever we draw a stereocenter like this, it is always referring to a specific molecule. It has a completely different meaning if it is rotated 90 degrees or if any of the two groups are swapped. Here's an important example. D-glyceraldehyde, the simplest carbohydrate, and L-glyceraldehyde, its enantiomer. Remember, lowercase d and L stand for dextrorotatory and levorotatory. Now here we have a capital D and L, and they actually mean the same thing for these molecules only. On any other molecule, the capital D would indicate that the highest numbered chiral center looks like D-glyceraldehyde, meaning the OH is on the right of the Fisher projection. More on this later. The D-glyceraldehyde line angle structure is shown, and the ball and stick model shown in the bottom left matches it. In order to make the carbons point away from ourselves, we need to rotate the molecule 90 degrees to the right along a vertical axis, which is shown immediately to the right of the molecule. The aldehyde is position 1 at the top, and the achiral CH2OH group is at the bottom. The other two groups are an OH and an H. In this view, the OH is on the right, so it ends up in the right of the Fisher projection. Again, anytime the OH is on the right, that's going to be a D carbohydrate. L-glyceraldehyde's Fisher projection is derived from its line angle structure identically. It can also be derived from the Fisher projection for D-glyceraldehyde. All you have to do is flip everything from the right side to put it on the left side. So L carbohydrates will always have their highest numbered chiral center with an OH on the left, as opposed to D's, which have their OH on the right. In Fisher projections, we are always thinking about the carbon chains as pointed away from us. However, line angle structures alternate back and forth. We'd have to look at a different side of the molecule every point along the way to envision the correct Fisher structure. If the molecule were actually arranged the way it is shown in a Fisher projection, it would need to be in a circle. The top left structure and the top center structure are both line angle versions of the same molecule, and so are the ball and stick models shown below them. When we arrange a molecule in a circle, it should look exactly like the Fisher projection. Envision rotating the molecule in the bottom right of this slide, the one that has my hand on it, 90 degrees to the right. And you can see that the positions of the green spheres will match to the positions of the OH in the Fisher projection. Now it's your turn to try some of these Fisher projections. There are 4 carbohydrates shown, and I want you to try to generate the Fisher projections for each one. Identify how many chiral centers you actually need to draw, and then write out the structural formula for the other parts of the molecule that are achiral. Remember that all of the carbon chains, which are vertical, should be assumed to be pointing away from you, and all the side chains should be assumed to be pointing towards you. So you have to think about how you're looking at each one of those carbons to orient yourself. These are the correct answers. Notice that some of these have their highest number chiral center with the OH on the left. Those are L carbohydrates, and only the final one on the right has its OH on the right, and that's D-tagatose. That's the only D carbohydrate that's shown there. We can use Fischer projections to quickly see relationships between molecules. Carbohydrates of the same size are all isomers of each other, and most of these are actually diastereomers. The figure shows all of the D carbohydrates that have an aldehyde as opposed to a ketone. Among the D carbohydrates of the same length, every one has some but not all flipped. The L carbohydrates are enantiomers of the eponymous D carbohydrates, which makes sense. If all the chiral centers are flipped, then the last one that determines whether it's D or L will also be flipped to look like an L-glyceraldehyde, making all the enantiomers L enantiomers. Finally, some carbohydrates only differ at one position. Each of the pairs above a branch in the tree, as shown, are epimers. Stereocenters, as we just saw, are an important part of carbohydrates. They also show up in many of our biological molecules, including medicines. Sometimes these stereocenters need to be arranged in a certain way to give the desired medicinal activity. Here are some examples. For practice, try to locate the stereocenter or stereocenters on each of these molecules. The top molecule is zopiclone, sold under the trade name Imovane. Zopiclone has one stereocenter, the carbon with a squiggly bond to an oxygen. We draw a molecule this way with squiggly bonds to specify that we have a racemic mixture. Remember, that means an equal mixture of both enantiomers. However, only one enantiomer is active for zopiclone, but both can give side effects. So a better known drug is S-zopiclone, which only has one S enantiomer. S-zopiclone is a hypnotic, non-benzodiazepam drug, better known by the trade name Lunesta. I think the slogan goes something like, "I sleep better with Lunesta." Because it is enantiopure, that is, it only has one enantiomer, Lunesta has lower doses and also less side effects than zopiclone. The molecule ethambutol has two different stereocenters. Both need to be in the correct form for this tuberculosis drug to work. Ibuprofen is sold as a racemate. Hence we recognize the racemic name, because there is an isomerase that converts the less active form into the more active form. The active form is dexibuprofen, which, as you might guess, is named as such because it rotates light to the right in the dextrorotatory direction. Fenfluramine is a drug with only one active enantiomer, while the other is inactive, meaning that it has no noticeable activity or side effects. The drug is an anorexiant, a weight loss drug that reduces appetite by releasing serotonin. Turns out fenfluramine also causes heart valve defects, so it's no longer marketed. Norepinephrine, which is a neurotransmitter closely related to epinephrine or adrenaline, is produced and marketed in enantiopure, just like it appears in the body. Only this form is active. L-DOPA is intended to mimic the function of this neurotransmitter to treat Parkinson's disease. For this reason, it must also be enantiopure. It only comes in the, you guessed it, the L form. Thalidomide is a drug that historically was used to treat morning sickness. There's only one active form, but the other form causes birth defects, which is a huge problem for a morning sickness drug. A bigger problem, the nitrogen can racemize, and the active form becomes the poisonous form. Some molecules, like dexamethasone, have many chiral centers. Dethimexazone is a corticosteroid with 8 chiral centers. We mentioned earlier that all carbohydrates are labeled based on the relationship to D-glyceraldehyde at the highest numbered position. Historically, longer carbohydrates were formed from D-glyceraldehyde by adding on groups to the aldehyde. So what used to be the aldehyde becomes the new alcohol, and an aldehyde gets added on the end. The last chiral carbon then never changes. However, the molecule's identity as D has nothing to do with the rotation of polarized light anymore. We talk about D and L amino acids in the same way as carbohydrates, except the aldehyde is replaced by a carboxylic acid and the alcohol is replaced by an amine. So anytime we have a D amino acid, the amine is on the right of the Fischer projection, and anytime we have an L amino acid, the amine is on the left of the Fisher projection. Interestingly, while most naturally occurring carbohydrates are D, most amino acids are L.